gentlemen, complex numbers. What we're going to be looking at today is the first part of complex numbers, representing complex numbers in Cartesian or rectangular form. Some of you might have had a go at this before on your BTECs or whatever. I know someone has, because they actually used them in the science assignment, even though I hadn't taught them. But that doesn't matter. It's good. Alright, so we're going to look at what a Cartesian complex number is. We're going to look how to add and subtract Cartesian complex numbers. I'm going to look at multiplication and division for a complex Cartesian number. Anyway, right, just get your calculator out. What happens if you try to calculate those three? Sorry? Yeah, your calculator's probably dealing with that as a complex number. I don't know. Just come to that. Yeah. Yeah. Math error to all those, yeah? Because there isn't a number, any number that you can multiply by itself that will give you -1. Yeah, that's why. Because that's what the square root is, isn't it? What number do you multiply by itself to get to the number that's inside the square root? So square root of 9 is 3, for instance. But there is no number that you can put inside and actually end up with -1, -3 or -14. So what they do, they have what's called an imaginary number. For engineers, we use J as being equal to square root of -1. Mathematicians use R, okay, because that conflict with the widespread use of complex numbers in electrical engineering, where we use I for the current. You choose the next available alphabetical letter, J, for complex numbers in engineering. So that's just a technicality. If you see I used, as in your calculator, we substitute J for that. Alright? So you'd represent these complex roots as J, yeah, or 1 times J. This would be 3J, 14J. Yeah. All right. Also, you'll see some textbooks will put the J before the number. So that one would still be J. There's J times 1, J3, J14. It's quite common. I tend to go with that way. I like to have mine that way round, but that's equally as good, and most people would understand still what you're talking about. So you can either have the J before or after the constant in front of it. Alright? So we end up representing complex quantities in what's called Cartesian form. We're also, that's there for completeness at the moment. Next week we'll be covering the polar representation of a complex number. Okay, so for this week we're working on a Cartesian representation. Next week we'll move on and we'll represent in polar form, and then we can work with both. And there's a convenience to these ones being easier to add and subtract, and polar being easier to divide. Alright, so we'll come on to that next week and the week after. Alright, we represent quantities and we can represent vectors, if you like, and more about those later, in terms of a real axis, which is the horizontal normal x-axis that we have, and an imaginary axis, where we'd represent these axes by the terms, for like 1 or a positive number that way, negative normal number to the left, a positive j amount upwards, and a negative j amount downwards. And a vector like so is represented by how many we go across, that's the 4, so how many we go upwards, plus 3j. So it has a real component, the horizontal axis, and an imaginary component, the vertical axis. Over here, we're going -4 on the x-axis, and then plus 3 upwards. So it's -4 plus 3j. In the third quadrant, so this is the second quadrant, this is the first. So in the first quadrant, both terms are positive. In the second quadrant, the real term is negative, the j term is positive. In the third quadrant, the real term and the j term is negative. And then in the fourth quadrant, the real term is positive, the j term is negative. So in those two parts, you can represent any angle and vector length around the whole 360-degree circle. All right? And then we can do the complex maths as well. So this will help us with AC electrical calculations, because we can have these forms eventually when we've done both forms that we can represent AC quantities in, right, where they have a length and an angle. Everybody happy with that so far? Yeah? So, doing some math with these complex numbers. Addition and subtraction. Two complex numbers are added or subtracted by adding or subtracting separately the two real parts and the two imaginary parts. So if we have, for example, Z1 is equal to A plus BJ, and Z2 is C plus DJ, then it equals A plus C. So we add the two real parts together, we add those two together, and then separately add those two together. Yeah. So we do the two parts separately. And if we're subtracting, we subtract two real parts and we subtract two imaginary parts, again separately. Alright, so proper example with numbers. If we're adding 2 plus 3j to 3 minus 4j, that's 2 plus 3, the two real parts, and 3j plus 4j, the two imaginary parts. So 2 plus 3 is 5, and 3j minus 4j is minus 1j, or just minus j. Yeah? 2 plus 3j take away 3 minus 4j, so we've got 2 minus 3 is minus 1. And we've got 3 minus minus 4, that bit there. So you have to be careful with your signs of your numbers. There's a double negative there, means you add. So that's minus 1 plus 7j. Yeah. All happy? Yeah. Now, you have already seen this in essence, but you can also add these and subtract vectors graphically. So you could draw a scale diagram, and that's all quite often worthwhile just sketching the two vectors that you're adding together if you're unsure, and seeing where you think they would come. For instance, if we're going to add p being equal to 2 plus 3j, so we're gone 2 across and 3 up, we're going to add that to 3 minus 4j, so we've gone 3 across, minus 4 down. We can complete the parallelogram of those two vectors and find the resultant in there, which is 5 across minus 1j. So we could, can you see by sketching that on an axis, if you're unsure, you can see whether you're in the same quadrant and whether you've got the right result. All right. If you want to subtract two vectors graphically, here's our p2 plus 3j. That's plus 3 plus minus 4j. So we've got to go in the opposite direction. Minus 3 plus 4j to get the negative vector. It's a little bit more difficult to understand, that one. So we want to add us down here, we want to subtract it, we've got to go completely the opposite direction. And then again, complete the parallelogram, and we've got minus 1 plus 7j over there. So just to show you that you can sketch these vectors onto a Cartesian axis, just to check your answers if necessary. So, have a go at those two. Given that Z1 is 2 plus 4j and Z2 is 3 minus j, determine what Z1 plus Z2 is, Z1 minus Z2 and Z2 minus Z1. Alright, have a go. Right, lads. Hey, we're looking at 2 plus 4j. I'm going to add it to 3 minus j. Yeah. So we got 2 plus 3, 5, and 4 plus minus 1 of j. Yeah. B, Z1 minus Z2, so that's 2 plus 4j minus 3 minus j. 2 minus 3 is minus 1, and 4 minus plus 5. And then the last one, C, which is 3 minus j minus 2 plus 4j, 3 minus 2 is 1, minus j minus 4j minus 1. Yeah, you can have the j first. Yeah, either way round, doesn't matter. And I think that's what I said earlier, actually. Yeah, back here, when I first introduced j, but I said some textbooks will put it that way round. It doesn't matter which way you put it round. Alright. Yeah. Right, next bit, gents. Multiplication of complex numbers is achieved by multiplying out of brackets and using the fact that j squared is equal to minus 1. Okay? Just going to qualify that. J squared. What we're saying is it's j times j. Yeah. Because what we're saying is j is equal to the square root of minus 1. So it's square root of minus 1 times the square root of minus 1. We multiply square root of a number by itself. What happens? You get that number. Because if we think about it, if we do square root of 4 times square root of 4, square root of 4 is 2. 2 equals 4. Square root of 9 times square root of 9. 3 times 3 equals 9. So if we square j, we must end up with minus 1. So j squared equals minus 1. What do you think then j cubed is? What j squared is minus 1. What is it now? If j squared is minus 1. This bit is minus 1 times j times j. Minus 1 times j must be minus j. It's not equivalent to 1. Minus j equivalent to 1. Minus j. I'll go through that again. You can write j cubed, can you not? As we have agreed that j squared is minus 1. Yeah? Do you agree that I can write j cubed as j squared times j? Yeah? And this bit, we've already said, is equal to minus 1 times j must equal minus j. You can't do minus 1 squared like that. What are you saying? Yeah, it's not minus, it's not j squared, is it? Why are you squaring that? You're not doing it right. I'm trying to use your calculator to see what I'm doing. I'm not being funny, but we're doing j squared, which we know is j times j, except that equals minus 1. So j cubed we can write as j squared times j. Everyone agree? J squared bit is worth minus 1. The j on its own is worth j. So minus 1 times j must be minus 1. And that's where we are on our axis, remember? Cartesian axis, we've got 1 there, or whole numbers, positive whole numbers there, minus whole numbers on that left to right axis, right to left axis, plus j upwards, minus j down. Yeah. You then multiply by j again. Minus j times j would be 1. Alright? The important thing is this fact that j squared is equal to minus 1. Right? It comes up in multiplying out and dividing complex numbers. So let's have a look at this example. We're going to do 3 plus 2j. We're going to multiply it by 4 minus 5j. And it is worthwhile putting these in brackets. Yeah, if that's what you call it, banana method. You multiply everything in the left-hand bracket by everything in the right-hand bracket. So 3 times 4 is 7. 3 times minus 5j minus 15j. 2j times 4j is plus 8j. 2j times minus 5j is minus 10j squared. We multiply, not add. So we'll multiply out the brackets. What's that? Well, 3 times 4 is 12. 3 times minus 5 is minus 15. 2 times 4 is 8j. 2j times minus 5j, 2 times minus 5 minus 10 times j squared. Yep. So we can collect like terms. So we got one constant on its own here, 12. Yeah. We've got minus 15 plus 8 is minus 7. J. Yeah. And here we've got minus 10. And remember, what else can we write j squared as? Do that like that on the end there. Okay, so then the page, we've got 12 minus 7j minus 10 times minus 1 is minus 10 times minus 1 is plus 10. The effect of that j squared on the end there is it changes the sign here always. So if that sign is positive, j squared makes it negative. Negative makes it positive. But it makes that end term another constant that we can add to this 12. So it's 22 minus 7j is the answer. Right. So the j squared becomes a minus 1 and effectively changes the sign of this last coefficient, last constant. So it gets rid of the j squared part, changes that sign. No, that's done now. So those two complex numbers multiplied together equals 22 minus 7. So on the next page, I believe you've got a couple to try, yeah. So the first one is 1 minus 3j times minus 2 plus 5j. The second one is 3 multiplied together. What you'll have to do there is take your result from z1 times z2 and multiply it by z3. Alright? Okay. Yeah. Right, gents. So z1 times z2, so we'll talk about 1 minus 3j times minus 2 plus 5j. So we do the 1 times minus 2, minus 2, 1 times plus 5, 5j, minus 3 times minus 2, plus 6j, minus 3j, plus 5j, minus 15j squared. That comes together as minus 2 plus 15, because that j squared turns that into plus 15, so that's 13, and plus 5 plus 6 plus 11. Yeah. And then the second one is multiply that result, so that's 13 plus 11j by minus 3 minus 4j. Must be careful with these negative numbers, the different signs. So that's 13 times minus 3 minus 39. 13 times minus 4 is 52 minus 52j. Minus 33j, 11, and minus 44j squared. Yep. So we're minus 39 plus 44 is 5. And we're minus 52 minus 33 minus 85. So multiplying two Cartesian or rectangular complex numbers together, relatively simple. We must remember that one fact, j squared is equal to minus 1. That has the effect of changing this sign, in this case from positive to negative. And it gets rid of that j squared sign. Alright? Everyone happy with that? So, moving on then. If we're going to do division, we need to know about what's called the complex conjugate of a Cartesian complex number. That's what I'm talking about. Right? What it is the complex conjugate of a rectangular complex number is found by changing the sign of the imaginary j part. So, the complex conjugate of 3 plus 2j is 3 minus 2j. The complex conjugate of minus 5 plus 4j is minus 5 minus 4j. We're just changing this sign either from positive to negative or negative to positive. So the complex conjugate of minus 2 minus 8j is minus 2 plus 8j. Complex conjugate of 6 minus 3j is 6 plus 3j. Multiply out those complex numbers and get a result. Okay, so see if you can see the general rule. You've just been doing multiplication. See what happens when you multiply the complex number by its complex conjugate. Got? Yeah? So how am I doing it without... It's the two numbers. Two coefficients. Yeah? So looking at the general rule, we're doing a plus bj multiplied by its complex conjugate, a minus bj. If we multiply that out, we end up with the a squared plus a times bj minus a times bj minus a minus bj squared. B squared, j squared, sorry. Yeah, these two translate. That j squared changes that sign to a positive, so it equals a squared plus b squared. So multiplying by the complex conjugate cancels out the j, the imaginary part, in the result, and the result is the two coefficients of the real and imaginary parts squared and added together. So just by looking at that, you can very quickly do the two numbers squared and you've got the result of that multiplying by complex conjugate. But more importantly, where is that useful? That's useful if you want to divide two complex rectangular numbers. Right? This is what we do. So, if we want to do division of complex numbers, we achieve that by multiplying multiplying both the denominator and the numerator by the complex conjugate. Effectively what we're doing is multiplying it by 1. So we multiply the complex conjugate of the denominator with, so we multiply top and bottom by 3 minus 4j. Yeah. Any number divided by itself is equal to 1, yeah? So we've multiplied that term by 1. In other words, we haven't changed it whatsoever. Alright? But what happens when we multiply complex number by its complex conjugate? We get rid of the j term. So that bottom half of the result we can do straight away. 3 squared is 9, plus 4 squared is 16. Bottom line is 25. Yeah, so even if they're more difficult numbers than that with decimal points, you can still square them both and add them together. Alright, and then the top line is 2 times 3, 6, 2 times minus 4 is minus 8j, minus 5 times 3, minus 15j, and minus 5 times minus 4 is minus 20j squared. And then we can go down the route of simplifying that top line. We know what it does. J squared changes this sign to a plus. So that's 26. Is it not? Hang on. No. Yeah, 26. Hang on. This is plus 20. That's minus. Minus 5 times minus 4 is plus 20j squared. So we got that j squared changes that sign to a minus. That's 6 minus 20 minus 40. Minus 8 minus 15 minus 23, all divided by 25. Yeah, and then we can do that division, so we can do this division of these constants separately if we want to. Minus 14 over 25 on my calculator, minus 0.56. Not sure if I've rounded it or not. And minus 23 divided by 25, I got down as minus 0.92. go. Just check this, please. Summarise that is, we take our two complex numbers that we're going to divide, got a numerator and denominator, we multiply the top and the bottom by the complex conjugate of the denominator. The effect of doing that is to make the denominator an integer. Get rid of the j term, and that denominator is equal to these two numbers, 3 and minus 4 squared and added together. Yeah. And then we simplify the top multiplication out and divide each one by the denominator to get our final answer. Am I right with those two constants? The two significant things. Yeah. All right. So, if I remember it properly, there's one for you to have a go at. Right, some more to have a go at as well on the following page for further practice. More convenient at that stage, you can write the answer as minus 14 over 25 minus 23j over 25. If you want to keep it in fraction form rather than rounded. Yeah. That is exactly the same as do well round those decimals. So it can be, if you want to use it later on in another calculation, you might well want to leave it in that form. Yeah. Because that 3 minus 4j is the complex conjugate of 3 plus 4j. Yeah. But if you multiply, we know that if we multiply the bottom by the complex conjugate, we'll get rid of the j term. Yeah. But what we do to the bottom, we must also do to the top. Otherwise, we've changed the expression. Yeah. So if I multiply top and bottom by the complex conjugate, you're effectively multiplying by 1. So you're still ending up, all of that is equal to that without that, just times 1. Yeah? Alright? Well, we'll go through them both together. So, first one is 1 minus 3j over minus 3 minus 4j. We've got to multiply that by top and bottom minus 3 plus 4j. Yep. Bottom line becomes minus 3 squared is 9, minus 4 squared is 16, so the bottom line is 25. And the top line, 1 times minus 3, I'll do this pretty quickly, it becomes 9 plus 13j. Yeah. So you can write that as either 9 over 25 plus 13 over 25j. Or if you've divided it out as 0.36 plus 0.52j. Yep. All got that one. So, how are we gonna work the second one? If we write this out, we've got 1 minus 3j going to multiply that by minus 2 plus 5j. And then the denominator is those two added together. 1 minus 3j plus minus 2 plus 5j. Hang on, let's just take this. What did you say, Don? Thirteen minus... No, it's not 13 minus 1. 1 times minus 2 minus 2. 1 times 5 plus 5j. Minus 2, minus 3 times minus 2 plus 6j, yeah, and minus 3 times plus 5 is minus 15j squared. Right, bringing them together, that's minus 2 plus 15 is 13, so the constant is 13 plus 11j. So you do really have to watch your signs, yeah? And then we've got to add these two together, so 1 plus minus 2 is minus 1, and minus 3 plus 5 plus 2j. Yeah. So we've now simplified top and bottom by multiplying the numerator terms together and adding the denominator terms. Now we can take this solution here and do the division. So we've got 13 plus 11j over minus 1 plus 2j. We've got to multiply that by complex conjugate of the denominator, so we've got to multiply that by minus 1 minus 2j over minus 1 minus 2j. What does that do to the bottom line? 1 squared plus 2 squared is equal to 5. Yeah. And the top line is 13 times minus 1 minus 13. 13 times minus 2 is minus 26j. 11 times minus 1 is minus 11j. And 11 times minus 2 is minus 22j squared. J squared, change that to a plus, so that's 13 plus 22. Minus 13 plus 22 is 9. And minus 26 minus 11 minus 37j. All over 5. So that equals 9/5 plus minus 37 over 5j. And if you want to divide that out, I've got 1.8 minus 7.4j. Yeah. And then on your last page of your handouts, there are some further examples for you to practice and have a go at adding, subtracting, multiplying and dividing Cartesian complex numbers.